Maybe this morning you ground your coffee. Maybe you used a motorized vehicle to get here. You used man-made machines operating on the centimeter to meter length scale. It's been the dream of scientists for over half a century to take this development all the way down to the molecular scale. That's nanometers. A nanometer is 1 million times smaller than a millimeter. In here, we have some molecular machines, a molecular motor, a molecular muscle, a molecular memory, an elevator, and there's a molecular car. This amazing development is due to several ingenious chemical innovations. A machine needs movable parts and a mechanism to convert energy input to motion in a defined direction. So the first challenge for the chemists was to make something that can move. This one you may recognize from yesterday. This one won't do the work. It's beautiful, but it needs to be connected to something. One way to make a physical connection is this, somewhat more ugly, but here we have two wings that move relative to one another, but they're freely joined. There is no chemical bond between them. To make this one is a piece of cake. You can buy it at the local supermarket. This one requires some very clever chemistry, and this year's laureates have developed new synthetic strategies to make molecules like this with good yields. The second challenge is to convert energy input to motion in a defined direction. Here, the problem is that molecular systems have a strive to reach equilibrium and fluctuate around it in random motions. So here, the challenge was to overcome this, and the laureates took advantage of a molecular property called chirality, or asymmetry. So now you may be curious to see what these machines look like. I'm sorry, you can't see them. They are more than 1,000 times smaller than a human hair. So we need a magnifying lens, and I think my colleague Olof Ramström can help here.